So thanks a lot for the opportunity to speak here. It's a real honor. So today I want to talk about some high-dimensional contact topology. Everything I'll say today is joint work with Jonathan Bowden, who's in Monash in Australia, and with Fabio Gironella, who's now in Budapest. And the paper is up on the archive, so you can find it there. So my talk will consist of the following points. So I'll first talk a bit about what the results we have are. The second part is dealing with the construction itself, this Bourgeois construction. And the third part, if I have some time, is to sketch some proofs. Okay. So, results. So the story starts with the following. So let me first introduce some notation. So we have sigma, some Liouville domain. So it's some n-dimensional manifold with non-empty boundary in some exact symplectic form whose boundary is convex. And we've got, I'll denote by B the boundary. And I have some monodromy phi, which is a diffeomorphism, which is a symplectomorphism. And I will denote by M OBD this open book decomposition associated to the Liouville domain sigma and the monodromy phi as the following decomposition. So I have one piece which is the polar neighborhood of B, which is going to be the binding, and there's some mapping torus piece associated to this monodromy. Right, so this is my notation for an open book decomposition. So the standard picture is here's my binding, which is a codimension 2 submanifold of M, and around it I've got color neighborhood, and the fibers of the natural S1 projecting to S1 of the mapping torus come in radially, and they look like pages of some open book. So here's a S1 projection. Okay, and these things are important for contact topology because they're related to contact structures by work of Giroux. Right? So the first step part of the story starts with the following theorem due to Bourgeois in 2002, which says the following. So you start with some contact structure. This is a contact manifold. Say dimension 2n minus 1, and you take some supporting open book decomposition as above. Supporting in the sense of Giroux, right, that the contact structure is sort of in some sense adapted to the decomposition of my manifold M into these two pieces in a very specific sense. And these things always exist by work of Giroux. So associated to these two pieces of data, so my contact structure and an open book supporting it, Bourgeois constructs contact structure on the product of M with T2. Right. So this is some construction. Right? The motivation for this, of course, is at the time when this was done, was to construct explicit examples of contact manifolds in higher dimensions. So in particular, for example, if you start with the torus T3, which has some natural contact structure, you do this construction and you get contact structures on every odd dimensional torus, which at the time was unknown ever since work of Lutz in the 70s. So this was actually important at the time. And in terms of existence of contact manifolds in higher dimensions, so nowadays we know a very powerful theorem due to Bourgeois, Augsburg, and Emmy, which basically can be resumed in the statement that whenever the obvious topological obstructions for the existence of contact structures in higher dimensions vanish, then you indeed have contact structures in any dimension. But the thing about these contact structures, which always exist whenever the obvious topological obstructions are not there anymore, they satisfy H principles, right? So they're very flexible, they're more topological in nature. And so the first result I want to discuss today is in some sense that this construction goes in the orthogonal direction. So they're very much not the ones given by Bourgeois and Murphy. So that's the first result, which is, I'll just use this one. So the tightness. So before I mention the result, let me just mention some work by other people. We have the following by Lisi, Marinkovic, and Niederkruger, 2018, which basically it says that this contact structure can be tight, meaning not one of those given by Bourgeois and Murphy, so not over twisted, even though originally the original contact structure was over twisted. Can be tight, even this, if this is over twisted. One of these flexible contact structures satisfying this H principle. So this is one first observation. And the second one is due to Fabio Gironella, which says, well, whenever you start with a 3-manifold M, which has a non-zero first Betti number, then he gives you some supporting open book decomposition. So there exists some supporting open book such that the Bourgeois is it's more than tight, it's actually hyper tight. Which implies tight by results of Alves-Hofer in high dimensions and Hofer in dimension 3. I'm being here slightly sloppy with the notation. I mean, the construction depends not only on the contact structure itself, but also on the open book decomposition. So you could have two different open book decompositions for the same contact structure such that the associated Bourgeois manifold are not contactomorphic. So usually I will denote this by Bourgeois sigma phi whenever I want to actually talk about what the open book is. Okay. What? Hypertight means I can find some contact form for the contact structure such that the associated vector field does not have any contractible ray borders, which is basically what Hofer does, which he proves that over twisted contact structures satisfy the Weinstein conjecture. Okay, so the first result is theorem 1 due to Voden, Gironella, and myself. So this is from this year, 2019. There's basically that if you start with some 3-manifold, then the associated 5-dimensional Bourgeois is always tight. Meaning independent on what the original contact structure was and what the original open book was. So you can give it whatever. You can start with an over-twisted one, and you will always get a tight thing. In some sense, we know a lot of results in the literature that flexibilize a given contact or symplectic object. For example, you can start with a contact 3-manifold, you can add a Lutz twist, and it becomes over-twisted. Or you can take a Weinstein manifold, you can flexibilize it by stabilizing all the critical attaching spheres and make them loose, and then you get a flexible Weinstein manifold. This goes in the orthogonal direction, so it's more or less like a tightifying construction. The caveat is that now you're jumping in dimensions. And the other remark that I want to make is that this result is it's sharp with respect to taking branch covers. So you can already take a degree 2 branch cover of this guy, such that it becomes over-twisted. And in fact, this was the first construction of an over-twisted contact structure in higher dimensions was using this branch cover of a Bourgeois manifold. The first construction on a closed manifold was using this. Okay, so this contact structures have been around for a while, and people have wondered about them for a while. And it turns out that they're actually geometrically interesting. So they're not topological. They don't necessarily satisfy any H principles. So in principle, they're amenable to holomorphic curve techniques and rigid invariants. Okay. Good. Where's it? Any questions? So everyone knows that we have dinner at 6. Okay, good. So that in some answers the first question that you want to ask yourself whenever you have a contact structure: what kind of nature it is. So is it a flexible or not? So it turns out that they're rigid. So the second question that somehow you're interested in it has to do with the fillability. Given a contact structure, you're interested in whether it admits symplectic. If so, actually, how many? To diffeomorphism or symplectomorphism or whatever. So this is the second part, which has to do with fillability. So let me again mention some results. So we have the following result due to Mazot, Niederkruger, and Wendel, which says that basically if you start with a weakly fillable manifold, then the Bourgeois is also weakly fillable. So weakly here is some sort of weaker notion than the standard sort of strong notion, or if you start with something which is a Liouville fillable, in particular it's weakly fillable. And this says that weak fillability is some property which stabilizes under this construction. Okay. The second result, again by the same people, Lissi, Marinkovic, and Niederkruger, in some sense says if you start with some subcritically Stein fillable thing, which by results of Silivac is equivalent to the fact that M admits a supporting open book whose monodromy is trivial. Then the associated Bourgeois manifolds is Stein fillable. Where the open book that I take is the one with trivial monodromy. Okay, so Stein fillability, which is a very strong sort of notion of fillability. Stein manifolds are algebraic, they're complex, they're very rigid objects. Stein fillability is not really something that stabilizes, but it stabilizes under some fairly stringent condition on the original one. Okay. Okay, good. So what I want to talk about, what I'll be interested is in what's called the planar case, which is the case when you start with some 3 manifolds. And when now sigma is a two-dimensional surface, and I just ask that the genus of that guy is 0. So sigma is just some sphere without a bunch of disks. Okay. So this is a planar case, and in this case, there's a following theorem by Wendell, which says something about fillings of planar contact 3 manifolds. So you start with some strong filling of a contact of a planar contact 3 manifold, and then the conclusion is that W admits the structure of a left stress vibration. Which, when you take the boundary, I mean, you get the original planar open book. So inducing original open book at the boundary. So let me just draw a picture and see that, to make sure that we're all understanding what's happening. So left stress vibration is some, I mean, it's not really a vibration, but it's a vibration modulo some critical points on which the vibration looks like a holomorphic Morse function. So you've got some regular fibers, and then you've got some sort of potentially singular ones on which there's a vanishing cycle which vanishes over a critical point here. And then when you take the boundary, naturally you see an open book decomposition, right? Where here's the color neighborhood of the binding, which is now the boundary of the fibers, and then the other piece is just the mapping torus piece, right? So which fibers over S1, right? And so this theorem, in some sense, says that you start with something that you already understand on the boundary. You've got with this open book decomposition on the boundary, and then you do some moduli space stuff. You do some holomorphic curves, and the holomorphic curves go inside the filling, and they become fibers of a left stress vibration. Okay, so this is the content of that theorem. And the corollary of the theorem of Wendell is that when you start with some, what's called a minimal filling, in other words, if you start with some symplectic manifold whose boundary is M and such that it doesn't have any spheres or exceptional holomorphic divisors, so you can, or you blew down everything that was there, so you get some minimal thing, and this are in 1-1 correspondence with strong fillings. This is a planar. Of course, blowing up or down doesn't change the boundary, so of course you would expect some sort of minimality condition. And the second part of the corollary is that if you take a planar 3 manifold, then strong fillability is equivalent to Stein fillability. Because, well, basically left stress vibrations are naturally Stein manifolds. So they have some very strong rigid structure. Right? So they're holomorphic and so on. So you start assuming that your planar contact 3 manifold is fillable, you upgraded the filling to some very nice category. Okay. Good. So what I'm interested in this setup is I want to understand how much of this picture stabilizes when I take the Bourgeois contact structure of a planar contact 3 manifold. And it turns out that the answer is rather surprising. I mean, actually, you lose most of the fillings. So let me just state the result, which is theorem 2, which is again due to the same people, so Bowden, Gironella, and myself. You start with a planar contact 3 manifold, where phi is now the monodromy of an open book. And then the result is that the associated Bourgeois is strongly fillable if and only if the monodromy is trivial to start with. So, in other words, you take all this very nice this picture, you stabilize it, and you lose most of the fillings. You only get fillings in the most trivial of cases. And in this case, of course, you can write it down. It's just a product, just as the page times d star t2. Right? So the filling for phi, the identity is just a product of the page sigma times d star t2 with its product structure. Okay, which is actually a Stein manifold. Well, if sigma was Stein to start with, which you can always assume it is. Okay. So, corollary of this is in the planar case, if you start with a monodromy which is a product of positive Dane twists, which I didn't say so, but you know, this is the monodromies that you see precisely at the boundary of a Lefschetz variation. So if you start with something like this, which is not the identity, then the associated Bourgeois manifold is weakly but not strongly fillable. So weakly but not strongly fillable contact 5 manifolds. It's weakly fillable because, well, originally if you start with a monodromy like this, then the contact 3 manifold is the boundary of a Lefschetz variation, whose the monodromy determines the Vannigen cycles and so on. So in particular, it's weakly fillable. That property stabilizes, so the Bourgeois is also weakly fillable. And it's not strongly fillable because of theorem 2, assuming that this is not the identity. Okay, so the remark here is that this kind of contact manifolds, you know, weakly but not strongly ones, were originally first constructed in higher dimensions and in dimensions greater than 3 by Massot, Niederkruger, and Wendel, and those were previously the only examples known. Also in dimension 5, and also smoothly the product of some 3 manifold with T2. The thing is that those examples constructed are associated to a manifold M which is never planar, because they fit into some sort of co-filling with disconnected contact type boundary, and those are never planar by a result of Fettenauer. So this result, this contact 5 manifolds are strictly not the same as the ones by Massot, Niederkruger, and Wendel, and in some sense they're more abundant. It's easy to say, easy to quantify them in some sense. You take some monodromy like this on some genus 0 surface, and you get an associated contact 5 manifold satisfying this. Okay, so in some sense they're quite abundant, and it would be interesting to actually construct them in any dimension. Perhaps by a construction like this in any dimension. So those examples are actually not known to exist so far.
And just the difference between weak and strong is that the primitive extends to the interior?
No, I mean, so the definition of weak fillability in higher dimensions, well, in dimension 3, it's just the symplectic form restricted to the contact plane is positive, right? Which is weaker than strong fillability. Strong fillability is you have a Liouville vector field which is transfers to the boundary and so on.
So the Liouville field extends to the interior?
Yeah, no. The Liouville field does not have to extend to the interior in the strong case. If it extends to the interior, that's a Liouville field. Yes. Strong is just the Liouville vector field is defined near the boundary. Weak,
Just in the color
yes. Weak is just you don't necessarily have to have a Liouville vector field at all. And yeah, in high dimensions it's a bit complicated to say what the definition of weak is, but it's definitely weaker than strong, and hence the name. Okay. Yes. Okay. So any questions? No. I mean, also another corollary is that we also have a stabilization of the corollary by Wendell. So strong fillability is equivalent to Stein fillability in the planar case, right? Which I mean is I've never seen any statement like that in high dimensions so far. I mean, maybe it's a bit for the specialists, but anyway. So and to finish with a part of the results, let me mention the following application, which is perhaps more appealing to most people here in the audience, is the following. And it starts with the following observation. The observation is that you take the unit cotangent bundle of Tn with its standard contact structure, sort of given by the boundary of the unit disk cotangent bundle of Tn, which is naturally Liouville Stein manifolds. And this, which is a very, very standard sort of contact structure known to many people, is actually one of these Bourgeois guys. This Bourgeois associated to a page which is d star t n minus 2, I think, and trivial manager. Okay, so we know that this is Stein fillable, and this is reflected in the fact that you have trivial manager. Okay. And this observation is nice because then I can use all the techniques from the previous theorems to prove the following, which is theorem 3. Which says that this manifold, which we know admits sort of a canonical Stein filling, that's actually the only strong filling up to diffeomorphism. So admits a unique strong filling up to diffeomorphism. In other words, if you give me any other strong symplectic filling of this contact manifold, then it's diffeomorphic to the unit disk cotangent bundle of Tn. Okay. Sorry. Yes. Thank you. Strong admits a unique symplectically spherical. Yes. Thank you. So symplectically spherical means basically there are no sort of holomorphic spheres, or I mean, I don't know if there exists such a notion of blowing down in high dimensions, but I'm just assuming that, yeah, basically that symplectic form manages on pi 2. Yeah, in this case, we only have one such filling. And this, in dimension 3, when n is 2, Stip 6 already proved uniqueness of the homeomorphism type, and then this was upgraded by Chris Wendell to symplectomorphism type. So we know that this guy in dimension 3 admits a unique filling minimal, right, which is the word replacing symplectically spherical, up to symplectomorphism. So the boundary remembers the symplectic structure on the interior, which is very, very strong. In high dimensions, we don't really have much technology in order to be able to say that, but we can say things up to diffeomorphism. And the sort of the keyword, the important keyword here is the S covariism theorem. Okay. Good. And I should also mention that this result was also independently obtained by Geiges and Kai Semic and Kwon. They put it up on the archive after we did, and I had a look at it, and maybe I should talk to them because the proofs looks quite similar to me, but maybe I should talk to them before saying anything that goes on videotape, but whatever. Yeah. Good. So any questions on the results? No? Okay. So let me sort of actually tell you what the construction is and rephrase it in some terms which makes it approachable to holomorphic curve techniques. So this is part 2. So let me tell you what the Bourgeois construction is, viewed in some different lens as to the original way the Bourgeois did it. So I want to think of this as in the following way. So, smoothly, this Bourgeois manifold is just, you take the open book associated to this abstractly and just take the product with T2, right? And this, by sort of the way that I wrote it down, has 2 pieces, right? And what I need to do is I just need to multiply with T2 each of them. So I've got my D2 here, and there's B, the binding, and then I take the product with T2. And one of the things that I want to do is I want to think of this as the unit disk cotangent bundle of T2. And the contact form that I'll write down is actually in some sense split. So we've got a piece which is lambda. Lambda here is the Liouville form in sigma, restricted to the binding, plus the standard contact form, the standard Liouville form in here. And there's this piece, and there's another piece, which is corresponding to the mapping torus piece, which looks like, well, there's some fiber-wise version of lambda, which is this denote by lambda again, plus there's a cosine theta dx plus sine theta y dy. So there's some formula here, but this is usually called the standard contact structure on T3. So there are 2 pieces, and somehow the contact form is adapted so that it's split. And I want to think of this first piece as fibering trivially over d star T2 with a standard Liouville form. And I want to think of this as fibering over S1 times T2, which is T3, with its standard contact form, which is the convex boundary of the base of the other fibration. Right? So there are 2 pieces. The first piece is a contact fibration over a Liouville domain. So the fibers are contact, which is B. And on the other piece, the roles are reversed. So the fibers are sigmas. So this is a Liouville fibration over a contact manifold. And they're glued in some compatible way. Right? And the contact form is adapted to these 2 fibrations in the sense that the contact form splits, at least up to isotopy, right? And this is what I like to call a decomposition. So it's a supporting spinal open book. Spinal, basically, well, this notion generalizes the notion of an open book. An open book I can also think in this way, like 2 fibrations glued together. So this is a bit more general. And this abstract notion has some notion, which is basically this sense of supporting a contact structure. So the contact form sort of is adapted to the geometric decomposition. Okay, and also the wave dynamics is also adapted to it. And I want to call this piece here, I want to call it MS, and call it the spine. And this piece, this fibration, I want to call it MP and call it the paper. Okay. So the paper is sort of foliated by pages, and the spine is foliated by vertebrae, which is the base of the spine. Okay, that's sort of jargon, but sort of suggesting. Okay. Good. And I want to claim that, well, I think this is a natural way of thinking of the Bourgeois construction. I mean, of course, this contact structure might we might have supporting open book decompositions because, well, they exist in general. But what the structure that you naturally see is this one. Just take the product with T2 and then write down the contact form, and sort of looks very adapted. Okay, so this is the first observation. And using this, is how I want to basically prove my theorems. Okay, so far is, well, we understood this construction more geometrically in some sense by some geometric decomposition, and I want to use that for the theorem. So let me sketch the proof of theorem 2. So let me remind you, we start with some filling of my Bourgeois. In the planar case, so this is a genus 0 surface sigma, and I want to show that phi is trivial. Okay. So I start with here's a picture. So here's my filling. Right, it's some symplectic manifold W, which I'm assuming is strong. So there's some Liouville vector field which points outward, so I can complete it with respect to that by adding some cylindrical end. So here's my Bourgeois in the boundary with its contact form, alpha Bourgeois, which is that one. And then I attach a cylindrical end, so this looks like boundary of W times 0 plus infinity times boundary of W with symplectic form, which is d e to the t of a Bourgeois. So over here, t is this coordinate. And I have my decomposition here of paper and spine. And what I want to do now is I want to construct a foliation of this cylindrical end and then say something about the moduli space of holomorphic curves that we'll obtain that will somehow test the topology of the filling. So I can actually construct some foliation of this manifold, which looks like this. So here what I do is I take my page sigma and I put it horizontally here at some fixed r direction. So here's some fixed t. And then once I cross over to the spine, I'm going to pick up some cylindrical end. So what this looks like is some Liouville completion of sigma. So topologically, this is just a copy of sigma with cylindrical ends, right? And they become asymptotic at infinity to r times the binding, well, times t2. So here's my binding times t2. And this is a bunch of Rabor bits. So over here, I've got a bunch of trivial cylinders. And these are holomorphic curves, which are asymptotically cylindrical over the binding. Okay? And they very nicely foliate this piece. Okay? And now one can show that sort of the moduli space that you obtain in here is actually regular and whatever. And then, so what these curves will want to do is they want to start coming inside the filling. Right? So they will go in. And then, and the point here now is that since I'm dealing with some at least 6-dimensional symplectic manifolds, I don't have positivity of intersections anymore. Right? So in dimension 4, positivity of intersection tells me two holomorphic curves, generically do intersect in a bunch of points, and those intersections are positive. Here, I'm dealing with some 6-dimensional thing, so I don't have that anymore. And so holomorphic curves will start to want to self-intersect or maybe intersect other curves. And I have no idea what happens inside the filling. But one of the important observations of this whole story is that I do have a lot of control of what happens at infinity. Okay. One of the claims is that actually I will see a foliation up there, which of course I don't see inside. So I will state that as a theorem now, but in principle what I get is a moduli space M of sort of holomorphic curves which look like sigma plus some cylindrical lengths. And inside this guy, which I will call, this guy usually I will denote by W hat omega hat. So it's a completion of my original fitting. Okay, so basically the proof relies on understanding the structure of this moduli space from which you can extract the result. Okay. And for the purposes of this talk, I will actually make some simplifying assumption, which we don't do in the paper, and which actually this simplifying assumption actually simplifies life a lot, which is we assume that the filling is symplectically spherical. Again, this means basically that there are no spheres, and this translates into the fact that there are no bubbles in this moduli space after I compactify. Okay, but in principle, after I sort of attach after I add the boundary, the SFT boundary of this, I could potentially see holomorphic buildings or nodal degenerations and so on and so forth. But it turns out that I don't. And that's the crucial ingredient of the proof. So the theorem has to do with properties of this moduli space. The first part has to do with the compactness, which says that this moduli space is SFT compact. In other words, I don't have any holomorphic building degenerations or nodal degenerations of curves in my moduli space. And this is the absolute key point of the whole story. Okay. So I mean, I don't see stuff like this. So I don't develop nodes. This doesn't happen. Okay. And this was precisely what in dimension 4 gave me non-trivial monotomy, because each node corresponds to a vanishing cycle, which corresponds to a Dane twist. Okay. And second property is this asymptotic foliation property. Which says that if I look sufficiently far away at infinity, close to the horizon, I actually see a foliation. So for every point P in some neighborhood of infinity, so here A0 is some really large, T0. T0 is some really large parameter in the Liouville direction. There exists some unique curve in the moduli space so that the curve U passes through that point. Okay. So for each point I have a curve that goes through it, and it's in fact unique if I look sufficiently far away, which of course does not happen, does not necessarily happen in the interior, because positivity of intersections is gone. Okay. And the third part of the theorem is that I can actually pin down precisely what the homeomorphism type of the moduli space is. Actually, it's a copy of D star T2. I can identify my moduli space with a copy of D star T2. Well, after I chop, well, I'm putting some stuff under the rug here, is that after I chop at some huge T parameter, I get some compact moduli space. Otherwise, I see a T star T2. In other words, the moduli space has a cylindrical end over T3. Okay, so maybe let me draw a picture. So what's happening is the following. So I consider M star, which is the marked moduli space. I take the curves in the moduli space and I throw in a marked point in the domain, which can vary in the whole domain. So this fibers over the original moduli space by the forgetful map, which forgets the marked point. And so the fibers are precisely the domains of the curves. But now I have an evaluation map to the completion of W. So this looks something like this. So here's a copy of D star T2. And I've got my forgetful map, so the fiber is precisely a copy of sigma. And here's my moduli space M, and here's M star. Right. And what's happening here is that I can naturally, this moduli space naturally has a boundary, and that boundary, because of the asymptotic foliation property, is the original manifold, the original Bourgeois manifold. Is diffeomorphic via the evaluation map to the filling to the boundary of W. So in particular, it inherits this spinal open book structure. It inherits some horizontal boundary and a vertical boundary, which is, in this picture, this is the horizontal boundary consisting of all the boundaries of the fibers. And this is the vertical boundary consisting of whatever fibers over the boundary of the base, which is a T3. And this is nothing else than the starting spinal open book decomposition. So this is MP, and this is M sub S. Right? So this, of course, because I started with my spinal open book at the boundary, fibers over D star T2. And the other piece, the mapping torus piece, fibers over T3, according to that geometric picture over there. And the moduli space, because there's no because it is compact, the fibers are all the same. So there are no degenerations or anything. In other words, this map here, which forgets a mark point, is a vibration. An honest vibration, not a lattice vibration or anything. And once I have this, if you observe, like, what's the monodromy of this vibration, of this paper vibration? It's just the original monodromy of the open book on the first factor and the identity on the second factor. And so in here, on the boundary, so here's my T3, right? On the boundary, the monodromy is the original one times the identity. But now, if I look at the cotangent fiber in here, I see an S1 on which the monodromy of the spinal open book is phi. But that S1 bounds a disk. And since I have a vibration structure, then the monodromy better be trivial. And that's basically the end of the proof. I mean, the key point, as I said, is compactness of the moduli space, which precisely rules out all possible non-trivial monodromies. And actually getting compactness is a very involved story, which involves two extra moduli spaces and a lot of headaches. So I won't have time to talk about that. If you're interested, we can discuss. And I think I started a bit late, right? So I have maybe like 7, 8 minutes. 10 minutes? Oh, okay. So this is the sketch of theorem 1, theorem 2. Let me just.
Can I ask in the compactness, I mean, it's some sort of index, or ultimately index?
No, I mean, yes, that's part of the story, but there's more than that. At least the way that we prove it.
I mean, I guess, where do you use the assumption that it's not just the original, that you're not in the four-dimensional case?
I mean, I don't think that's an assumption. I mean, I'm not sure what you mean, but what you, okay, I see, yeah, sure.
You don't do the bourgeois construction.
Yes.
You just look at the original.
So what's happening is that I start with my bourgeois thing. What I can do is I can there's this capping construction which generalizes Yasha's. So you do some cobordism, and what you see in the boundary is now a copy of S2 times T3. Okay, so let me just, you start with your guy, you sort of cap it, you add some handles, and here's a D star T2, which is your co-core, and the boundary is looks like an S2 times T3. And now I have a T3, which in dimension 4 I would only have an S1, right? So I have a S2 times S1. And when I complete this, right, the point is that the completion of the T3 has a lot of holomorphic cylinders which were not there in the 4-dimensional situation. I mean, the 4-dimensional situation I only see trivial cylinders. And here there's a whole moduli space, this sort of Wendell family of holomorphic cylinders. And you can use those together with the moduli space of S2s to conclude that after capping, sort of you've got W cap, that this guy has to be homotopy equivalent to D star T2 times S2. And now the point here is that there's only one spherical class. So if you saw something like this, you can cap with the cores, and you would see two spheres that intersect the co-cores. I mean, but you can't have that if you have this topology, right? I mean, that's what's happening. Yeah. Any more questions?
Yeah, can you be more precise about what homomorphic curves are in this modular space and what the almost complex structure you choose?
Okay. I could, yes. So this construction originally appeared in dimension 3. This is this holomorphic open book by a number of people, Chris Wendell and Abbas. You can just, you need to deform your contact structure. I mean, you start with your supporting contact structure. There's a Giroux form which is adapted to it. You need to deform your Giroux form such that it becomes tangent to the pages away from the binding. And now, sort of, because it's tangent, you can just take any J on the page, which makes that piece holomorphic. And then you need to add some cylindrical lengths. You need to basically the J is going to be adapted to this geometry. I mean, I could tell you more, but it's a bit technical. But you can just get your hands on that. You construct it by hand, basically, because I mean that's the only thing you can do, right? I mean, J is non-generic. Right? Yeah, and you can do this for any spinal open book. Actually, there's a more general notion. You can construct these foliations for any sort of even the dimension of the page can be whatever even dimension. So you have this foliation, for example, by hypersurfaces. Yeah, it's a very general construction. Any other questions? Okay. So if there are no other questions, I will maybe give a very brief sketch of the other theorem and then finish with that. So. So let me sketch theorem 1. So remember, we want to show that the Bourgeois is always tight when I start with a sigma being a surface, right? So I start with a 3 manifold and the Bourgeois, and I want to show it's always some very rigid contact manifolds. So the first input of that is the following strategy by Hofer and Albers-Hofer, which you can black box it in the following result. You start with a Liouville cobordism. So here's my Liouville vector field, and here's some contact structure, and here's another one. Then if this guy, if the guy downstairs is hyper tight, which again is some sort of dynamic condition on the brave dynamics, namely that the no contractible brave, or it's if the guy downstairs is hypertight, then the guy upstairs is tight. Okay, I mean this is a bit deceptive because tightness wasn't defined at the time that these people proved this. What was defined is the notion of Plastikstufe, and well, nowadays we actually know that having a Plastikstufe is the same thing as being overtwisted. So they proved that there is no Plastikstufe up here, and then use some Bishop family of holomorphic curves and study compactness and so on. Okay, so this is the first black box. And assuming this, so the proof has 3 steps. So the first step is the following. So we want to apply this. So first we need to understand when the Bourgeois contact structure is hypertight. Right? So the first question is, when is this guy hypertight? And answer to this is, well, if the binding, which is now a bunch of circles, right, has infinite order in the fundamental group of the original 3 manifolds, then the associated Bourgeois is hypertight. Okay, the whole point here is that somehow when you do the Bourgeois construction, the wave dynamics changes away from the binding. So the binding is still a bunch of wave orbits, but whatever was in the whatever orbits you had in the mapping torus piece are forgotten when you stabilize. So actually the wave vector field now points in the base direction, on the T3 direction. And orbits in there are automatically non-contractible. So that's the key for this. So let me just call this start phi, so condition on the monodromy. I'm gonna fix sigma, so this is a condition on phi. Which again is a topological condition, right? I mean, I reduce some sort of a dynamics condition to some topological one. And step 2 is a factorization lemma, which says the following. So every phi for generic sigma, which generics means whatever sigma admits a hyperbolic structure, every phi for generic sigma can be written as a product of 2 monodromies such that the condition star phi holds for both of them. Right? So in other words, the binding of the corresponding open books has infinite order in the pi1 of the corresponding 3 manifolds. And here there's no contact or symplectic anything. This is some hyperbolic stuff and geometric group theory and the mapping class group and so on. Okay, it has to do with the pseudo analysis and whatnot. But yeah, so that's why the generic condition, because you want to have some sort of pseudo analysis. The non-generic surfaces are dealt with hands-on, so I'm just gonna forget them. So this is step 2, and then right. So you take any monodromy and decompose it into a bunch of pieces such that the associated bourgeois are hypertight. So the missing part of the puzzle is a cobordism. So there exists some cobordism like this. Right. You take any bourgeois associated to any monodromy, there's a cobordism to the composition up there. And now, if you believe that if this cobordism were Liouville, then the proof is done, right? You start with the whatever monodromy, right? Like this, you have this cobordism. These two things are hypertight. Then the Hofer black box tells you that this is tight. Done. The caveat is that this cobordism is actually not Liouville. It really wants to be Liouville, but it's not. It's what we call pseudo-Liouville. So it's a strong cobordism with an exact symplectic form, but the Liouville vector field is not really inwards pointing at the negative ends, which is a headache. But the properties of the particular coordinate that we construct actually are barely enough such that the proof of Albers-Hofer goes through, which is the magic. I mean, so we were quite lucky in that sense. But modulo those technical details, this is sort of the end of the sketch. And I'm done with that.